Then the first condition is ext must be constant. Ext is constant and another one here, covariance sxt should depend only on the time difference or independent of t. It will not depend on time, okay? If you want, you can write this way, covariance xt plus s. There is one variable now, instead of writing two variable. xt plus s depends only on s. It's independent of the process, okay? That means what we want to say is, if you want to find covariance of x10 x12 and covariance of x110 x112, they must be the same. It will depend only on the time difference, that is s here. T is immaterial, whether it's 10, 20, 30, 40, as long as the difference is the same, or in terms of this t minus s, time difference t minus s. So here t minus s is 2, here t minus s is 2. So they should be the same. Okay, this is the definition. Expectation is constant, the average value should not change, and the covariance should depend only on the time difference s and t. That is what you need to check. Okay. Now covariance of xy is equal to covariance of yx. Even you can write this way. In both cases, we'll use this notation. These are auto covariances. Remember, in stochastic process, we use auto covariances. And if you take the same covariance x10, that will be variance of x10. If they are the same. Now from auto covariance, you can find auto correlation. So rho 1, rho 2, these are the notations. Rho 1 is gamma 1 divided by gamma naught. Rho 2 is gamma 2 divided by gamma naught. Here you write the definition for this and this. Remember, gamma naught is variance of xt. Gamma naught is covariance of xt here. You write 0, 0, 1, 1, 2, 2, it doesn't matter. And that is gamma naught. So if you divide gamma naught, you will get autocorrelation. Autocorrelation of lag 1. Autocorrelation of lag 2. Again, we will discuss more whenever we will consider an example, what are lag 1, lag 2 and how we can use this later. For time being, just remember the symbols, okay? Now, here you can write this as 2. You see the definitions in other books. they write 3, but 2 comes automatically from 3. Okay, so though this is a consequence of 3, but we will write it specially due to its importance. Again, in our material, this is called weakly stationary, which we can track mathematically. This is the weakly stationary. But remember, we consider only weakly stationary process here throughout this course, and for which you will see the word stationary. Okay, there is a general definition of stationarity. I must have discussed in the last class, but we don't use that. And I will give you an example later to differentiate between strictly stationarity and weakly stationarity. But remember, mathematically we'll use this one always, though this is weakly stationary, but in this course we will consider weakly stationarity only, and stationarity means weakly stationary all the time. So we will not worry about the stationarity in the strict sense. It has a definition. The statistical properties of x1, x2, whatever you find, after some time they should remain the same, whatever I discussed. Okay, that is there, but we have one example. Okay, through example we will see what is the real difference between these two. That I will not do in this class. Consider AR1 process. Consider AR1 process, and we will write here xt is equal to mu plus alpha xt minus 1 minus mu plus et. And this is a recursion relation, so you can find all these xt minus 1, t minus 2. You just put values here. It will be t minus 2 plus et minus 1. If you find xt minus 2, you will get xt minus 3 here minus mu plus et minus 2. So what you are doing is you are replacing by, in t minus 2 you are replacing t by t minus 2, you replace t by t minus 1, you will get this one. Then you put this one here, the value of xt minus 1 you can put here, and the value of xt minus 2 you can put here. Okay, we got already t minus 1, you put here, and then t minus 2 you put here, and this one you put here. That way if you do, you can track up to the first one. How? Let me write it here. So what you need to do is, you need to write xt is equal to alpha, or maybe directly you can find this one, this vector here, you put and cut, whatever you do, this minus this. Okay, there you can write this term, that means alpha multiplied by this one, you will get alpha xt minus 2 minus mu plus et minus 1. Okay, then what will happen? Plus et minus 1 is there. Now you replace this, that is here, xt minus 2 minus mu by this one in the next step. So here in the first step, xt will be alpha square xt minus 2 minus mu plus alpha et minus 1. Okay, I think this is t minus 2, sorry, this is t, this is et, this will not change. Here this will be et minus 1. Okay, so et. Once you get this, then replace xt minus 2 minus mu from this equation. Okay, you put this one, then you will get in terms of xt minus 3. Continue doing that till you go to the last one. Okay, and finally if you continue, you can check it. Xt should be equal to mu plus alpha power t x naught minus mu plus et alpha et minus 1 alpha square et minus 2 alpha t minus 1. Okay, then we have to check here once more. When you write power 1 here, you get et minus 1. Okay, so whatever is there, whatever power is here, that you need to suppose et means alpha 0 et minus 0. See, it's like this, the power, this one and this one, they should match. So if I write t minus 1 here, I have to write e1, not e naught. Check here. Okay, because this is our first term, we are going this way. We have started from et. Why we have started from et? Because this will be the last term. See, this will not change. So if you start from this one, the error term, and continue this way, what will happen is you will reach here. That is what you need to remember. Also, here the assumption in this chapter, et follows normal 0 sigma square. So the errors are here IID, okay, and mean should be 0, mean error should be 0 at each time, and the variance is constant. Variance from time to time, it should not change, constant variance, and 0 mean. Then what will happen when you find ext, you have to recognize this. When et follows normal 0 sigma square, then e of et should be 0 and variance of et should be sigma square. Okay, so then what will happen when you find this one here, mu is already there, e of mu will be mu, e of x naught will write there, plus alpha t is constant, will write e of x naught minus mu, e of mu is mu, then e of t is 0. So if you take expectation, the first error term will be 0, the second error term will be 0, and the last one will be 0. Multiplied the constants, so that will be 0. Finally, this will be our equation 1. And if you take variance of xt, okay, if you take variance of xt, variance of a constant 0, you write alpha t variance of x naught here, plus variance of et sigma square. You go on putting sigma square here, all error sigma square here. But when there is a constant, when you find variance, that alpha will come outside a square. Okay, so v of et will be sigma square, plus v of this one will be alpha square sigma square, v of this one will be alpha 4 e power t minus 2, alpha 4 e power e t minus 2 variance, that is sigma square. It will continue, and finally the last one, alpha 2 t minus 1, it will come out square. Variance of p1 is sigma square. So this is equation 2. If you want to write properly equation 1 and 2, you will get this way. So we'll write equation 1 and 2 within the box. Here E x naught is equal to mu plus alpha t E x naught minus mu. This is the first one, and the second one is V x naught, that is equal to, we can do a little bit work here. You take common here sigma square. If you take sigma square common here, 1 plus alpha square, that way you will get alpha square. Also you take beta. Okay, if I take alpha square beta, then you get 1 plus beta square up to beta power t minus 1 gp. Okay, this is a gp. Also I missed one thing here. This will be alpha 2t here. This will also come outside the power. I have to write alpha 2t here. Okay, so let me write 2t, and because there is an expression I'm after that, sigma square, if you add all these 1 plus beta square beta power t minus 1, it will be beta power t divided by 1 minus beta. Okay, and this will be 1 minus, in beta if you write alpha square, alpha 2t divided by 1 minus beta is alpha square, this way. So this is the first term, variance of xt. This is the first term I am written, first term. Okay, plus here the second one, this one we found here. If you multiply with this one, you get sigma square by 1 minus alpha square. That's fine. If you see the second one, that is actually sigma square alpha 2t divided by 1 minus alpha square. So from these two I want to take sigma alpha power 2t common. Okay, this one I have written here, and from these two I will take alpha power 2t common. Then whatever expression I will get, I will write within the bracket. If you take alpha power 2t common, then what you will get, variance of x naught minus sigma square divided by 1 minus alpha square. Variance of x naught minus sigma square divided by 1 minus alpha square. See, I thought not to do this one derivation, not that important, but I saw in 1 or 2 exam questions they asked this. Okay, before, maybe they will not ask in future, it's open book now, but yeah, this is important for understanding also, initial understanding. Okay, now we'll consider these two. Forget every other thing. This is a very simple derivation, 3-4 line derivation. Okay, here I left this, right? Okay, so variance of xt is constant. Let me write this. ext is constant, variance of xt is constant, and covariance xt xs depends only on the time difference t minus s. We will erase every other thing. Though this is weakly stationary, okay, will not worry about this. We'll remember these three. Now expectation must be constant, variance must be constant from time to time, variance should remain constant. Not only that, covariance of xt xs depends only on the time difference. These are the three. Now if you see this one here, ex naught ext, again I am making a lot of mistake, right? Left hand side xt, let me change it. So ext is this, variance of xt is this. Okay, left hand side we have xt, ext variance xt. So now if you see this one, ext must be constant, variance of xt must be constant, the left hand side. But if you see, there is a t dependence. Okay, suppose if you find ex10, you will get something. If you find ex12, you will get something. That means the expectation of the stochastic process changes with time. We don't want that. So how that is possible? That is possible only when the t dependency will disappear. Okay, so at least to satisfy 1 and 2, what should happen? Property 1, ext should be constant. So if you take this, ex0 is mu. Sometimes you see notation mu naught for this one, mu naught is mu, and variance of x0 is equal to sigma square divided by 1 minus alpha square. Then this will be 0, this will be 0, okay, and then this will be mu, and variance of xt is equal to sigma square divided by 1 minus alpha square. So what will happen is, if ex0 is mu and variance of x0 is this, of course alpha mod less than 1, that should be also there. In these three conditions, okay, this is a special condition. In these three conditions, then what will happen? Expected value will be mu, variance of x0, that will be sigma square by 1 minus alpha square. So expectation constant, variance constant, at least two of the three properties I mentioned for stationarity are satisfied here. If these two conditions are satisfied, then covariance is there. Okay, we'll go to that later. So at least you have to see these three conditions. Now we'll turn it to the other side. We'll say, even if this is not satisfied, as long as alpha is less than 1, still this could be stationary, xt could be stationary in one condition. For large t, if t is large, okay, that means this might not be stationary now, but if you see a long time, then in future it will be stationary if star is satisfied. If alpha mod is less than 1, even if it's not stationary now, even if these two conditions are not met, if alpha mod less than 1, as long as alpha mod less than 1 is there, then this will become stationarity in the long run. That means what we want to say here is, this will be stationary in the long run even if it's not stationary now, because mathematically what will happen when t will tend to infinity, okay, let me write here, if this is satisfied, then what will happen? Limit alpha t tends to infinity, because alpha mod less than 1, okay, you take alpha half square like that, this will go towards 0. If you take alpha 2, then this will go towards infinity. Remember, if alpha you take 1 also, then it will tend towards 1 power t will be 1, not 0. Because alpha mod less than 1, then this will go towards 0. Not only that, the other one, if you see alpha 2t, that will also go towards 0. Limit t tends to infinity, alpha 2t, that will be 0. Then what will happen? Then this term will vanish anyway. So even if these are not satisfied, these two will vanish anyway by virtue of these two. Okay, in the whole expression you have alpha t outside, here alpha 2t outside. These are not equal. Suppose this is not equal to this, this is not equal to this, but this will become 0 after a long time. So again you will get these two. Okay, so remember, if these two are satisfied and alpha mod less than 1, that is fine. Even if these two are not satisfied, in the long run, okay, these two will become 0. So by virtue of these two factors, again these two will be 0, and finally you will have this one and this one. Logically, these two will become so near to 0, so small that this will not contribute, okay. Even if they are not equal, suppose you multiply by 0.00001, this will not contribute, this will very small, okay. 0 contribution, 0 multiplied by this, that will become 0. So what will happen? ext will remain constant, variance of xt will remain constant, at least first two are satisfied. And then we'll go to the covariance. This should xt minus k, we'll find this t plus k or t minus k, whatever you write, it doesn't matter. They should be the same, right? Because when you write this one for sigma gamma k, if you write plus then also gamma k, because we will see the difference, okay. So as long as alpha mod less than 1, as long as alpha mod less than 1, what will happen? If you see this one here, this will be mu, this will be sigma square divided by 1 minus alpha square. In the long run, okay, these two will vanish. That is what I want to say. E of xt will be equal to mu, and then vxt will be equal to sigma square upon 1 minus alpha square. These two will be satisfied, okay. In the long run, okay, if the other two conditions are not satisfied, this will happen in the long run, okay, when t tends to infinity. Now you consider this straight line and you think that presently there is a process which was running since long time, okay. Now when we reach here at 1 or 0, whatever you write, starting from here we can write 0. Starting from here, if you see forward, then what will happen? I mean, starting from here, it becomes stationary. It already becomes stationary because it has infinite history. We say this is infinite history. This is a technical one, infinite history. You see in some problems, okay, initially. Infinite history means there is a process which was running from a long time, okay. Now it becomes stationary already here. This is present. So there are two ways. Either you say if you start observing a process from now, if alpha mod less than 1, even if it's not stationary because the other two conditions are not satisfied, it will become stationary in the long run. In other words, you can say if there is a process running since long time, now it becomes stationary already, okay, then we'll check only this one for this kind of a process, okay, alpha mod less than 1. That is what you need to remember. And expectation of xt is constant mu, variance of xt is constant sigma square by 1 minus alpha square. Now let me find other things like this. Remember we started with this one, xt is equal to mu plus alpha xt minus 1 minus mu plus et. Then we'll turn it into another series yt where there will be no mu. So I will write yt is equal to xt minus mu, and I will put it here. Yt will be equal to alpha yt minus 1 plus et. Then it will be easier for me, okay. So I can find gamma 1 here. Gamma 1 will be covariance xt. Gamma 1 is covariance xt minus 1. Remember, this way you need to write all the time. In terms of yt we need to write, because we will consider this. Henceforth we will consider this one, the easier one. We will not try to complicate it. Okay, so gamma 1 is covariance yt minus 1. We will write this way. Okay, and gamma 2 covariance yt minus 2. You can write t plus 2 also here, because the difference is 2 anyway. T minus 2. Suppose you write gamma 2 covariance yt plus 2, then also it will be, I mean, if you take the difference this way, it will be gamma minus 2 and this will be gamma 2, right? So 2 minus 2, they are the same, because covariance of xy is covariance of yx. So we will not worry about these things here anymore. Okay, now this is covariance gamma t minus 1. This is covariance gamma t minus 2. And then you write gamma 3 covariance yt minus 3, that way. This is gamma 1, and in each case you have to write gamma t yt value. In each case you need to write yt value. Yt is alpha yt minus 1 plus ct, then yt minus 1, and the second one here yt alpha yt minus 1 plus ct, yt minus 2, and here covariance alpha yt minus 1 plus et yt minus 3. Remember, these are the white noise et, and et yt minus 1 covariance is always 0. Again, let me tell you here, if you consider covariance of x plus y z, it will be covariance of xg, then covariance yz, this way. Okay, these are the two. If you even write 2 here, the 2 will come out. These are the properties. So here you can separate these two. If you separate these two, okay, alpha yt minus 1 with yt minus 1, and then let me write the first one. Alpha I will take out, covariance of yt minus 1 yt minus 1, that is variance of yt minus 1. Let me write covariance of yt minus yt minus 1, that is variance of yt minus 1, and that is sigma square always. Remember, yt follows normal sigma square. Even yt minus 1 follows normal 0 sigma square. So if you find variance, it will be sigma square. Variance is sigma square. Okay, but et, when you find et with any previous values, that means if this is your timeline and you want to observe, you want to find the covariance between the error here and the previous values of the process. Suppose yt minus 1 here, yt minus 2 here, that way. This is t minus 1, this is t minus 2, that way. What will happen? It will not depend. Yt is independent of this. Can you answer why? Yt is independent of this because this is the shock. the random shock, the white noise here. In terms of the example, whatever will happen here, it is a part of that. Suppose I plan to give you 1 hour class today. I am not able to give you 1 hour class because there was a disturbance. Okay, so that I didn't know, I had no idea, right? So that error will come here. If I am able to give you only a 50-minute class, then the 10 minutes minus 10 minutes, that is ET. That was not known before. Here yt minus 1 is the time I spent with you at t minus 1. Here this is the time I spent with you at t minus 2. Today whatever I am spending with you, suppose I know that now yt. So a part of yt is the indeterministic one, yet. That has nothing to do with the past. That is why we say this is a random shock, white noise. Okay, this has no past dependency. All the errors, they will depend on this. So if you find the correlation of ET with yt minus 1 or the covariance, that will always be 0. So all of these will be 0. ET yt minus 1 covariance will be 0, ET yt minus 2 0, ET y3 minus 2 0, all these are 0. We'll use here. So if you use all these, then you will come to this. Okay, let me write once again. Gamma 1 will be alpha here. Let me change the ink. Okay, alpha here, and yt minus 1 sigma square, and the second one is 0 sigma square. And this one, if you see, yt minus 1 yt minus 2. Okay, you need to subtract this minus this or this minus this, it doesn't matter, that is 2 here. So if you find the covariance between t minus 1 t minus 2, the difference is 1. It doesn't matter positive or negative, always you write difference 1. Okay, so it will be alpha. I think I have to start from here once again. Now you need to find covariance of alpha yt minus 1 with yt minus 1. The first one, this one with this one. What will happen? You take alpha common, and yt minus 1 with yt minus 1 covariance, that you need to write. If you see left hand side also, I have written 1 here because covariance yt minus 1 I have written. Okay, if I write covariance yt, this will be gamma naught, gamma 0. If I write covariance yt minus 1, that will be gamma 0. So you will get gamma 0 here, and the second one is 0 anyway. Similarly, if you write here, you see the difference between t minus 1 t minus 2, positive or negative, we will write 1 only. So that will be alpha gamma 1 plus the second one will be 0. Okay, et yt minus 2, that is 0. If you write here t minus 1 t minus 3, difference is 2, alpha gamma 2 plus again there is a problem. Okay, this is alpha gamma naught plus covariance of et yt minus 1. Okay, that is 0. Yeah, that was fine, that is 0. And here covariance of alpha yt minus 1 yt minus 2, that will be alpha gamma 1 plus et with yt minus 2, 0. And here if you see the difference between t minus 1 and t minus 3, yt minus 1 and yt minus 3, the difference is 2 here. So alpha gamma 2 or minus 2, whatever you write, they will remain the same, plus 0. Now gamma 1 is equal to alpha gamma naught, gamma 2 is equal to alpha gamma 1, gamma 3 is equal to alpha gamma 2. Okay, let me write all. So remember, what is gamma 1? Gamma 1 is equal to alpha gamma naught, gamma 2 is equal to alpha gamma 1, gamma 3 is equal to alpha gamma 2. You continue this way. From here we'll write alpha, and gamma 1 you write alpha gamma naught. That will be alpha square gamma naught, and here alpha, in gamma 2 you write alpha gamma 1. That will be alpha square gamma 1, and in gamma 1 again you can write gamma naught, or what we can write is, in gamma 2 only we will write this. Okay, or in gamma 2 only we will write this. Already we got this one will write alpha square gamma naught, that will be alpha power 3 gamma naught. This one also you see. Now from these, gamma 1 by gamma naught will find. This is rho naught, rho 0, okay, alpha. This is rho 1, gamma 1 by gamma 0 will be rho 1, okay. This is rho 2. See this one, if you divide you will get alpha 3. This will be rho 3, rho 1, rho 2, rho 3, alpha square, alpha power 3, that way. And finally it will decrease. We'll see how it will decrease, because alpha more less than 1. Rho 1 is equal to alpha. Let me write rho 1 is equal to alpha, rho 2 is equal to alpha square. If you write rho naught, that will be 1 anyway, okay, because that will be gamma naught divided by gamma naught, that is 1. You write rho 3 alpha power 3, because alpha more less than 1, this is decaying, okay, this is decaying exponentially, and what will happen, it will go towards 0. If alpha more less than 1, it will go towards 0. These are the autocorrelations. This is 1, this is 2, this is 3, this is 4, and these are the autocorrelations, okay. This is alpha at time 0, suppose this is 1 here, okay, this is 1, this is alpha square, this is alpha power 3, this is alpha power 4. It's decaying exponentially, okay, this is decaying exponential. These are the autocorrelations. So what is autocorrelation of lag 1? If you want to know a bit about this, we have to see, suppose I write process like this, x1, x2, x3, x4, like this. Autocorrelation at lag 1, that means you see the link between these two, these two, these two, these two, that is rho 1, okay. Autocorrelation, not autocovariance. If I write autocovariance between x1 to x2, that is gamma 1. Autocovariance between x2 to x3, that is gamma 1, okay. What is gamma 1? Autocovariance, okay, autocovariance between x1 to x2, you write x2 to x3, same you will get gamma 1, because we say this will remain the same when the lag is same. Okay, when you talk about one time period, it should not be different. So gamma 1 means auto covariance between this to this, this to this, this to this, that way. The one time lag link, okay, relation. Gamma rho 1 means auto correlation, auto covariance, auto correlation. That is the difference. So auto correlation rho 1 means the link between the immediate points, okay, the values. So there is a link alpha. If you take alpha, suppose 0.7, there is still a 70% link. However, if you take 2 here, rho 2, that means we want to connect this way. We want to connect x1, x3, x1, x3, okay, 1, 3, then 3, 5, 5, 7, even 2, 4 also. So you take 2 lag, then compare. So if you take 1, 3 or 2, 4 or 3, 5, okay, all those will be gamma 2. From gamma 2 you will get rho 2. So rho 2 means 2 lag link. Okay, so then what will happen? There is high correlation. No, sorry, if you take 2 here, the correlation is decreasing. 3, the correlation decreasing. 4, the correlation decreasing. It should decrease. Then what will happen? It will decrease, it will decay, it will go towards 0. There will be no correlation at all. That means, in a sense, you can say slowly the link is disappearing. The link should disappear to be stationary. So if alpha mole is less than 1, remember we started with this condition, only one condition, alpha mole less than 1. Then what will happen in this condition? This will happen. Okay, so we'll visit this one once again later. Just now remember, suppose you record the temperature, okay, and you record the temperature monthly. This is suppose 2020 January, 2020 February, 2020 December, okay, 2021 January, 2022 February, 2022 March. If you write that way, then what will happen? With time you have to see, you have to charge one second computer. So if you observe this way, then what will happen? We'll draw one. It will not, if you take lag one time period, that is 1 month, okay, between January February there is some link. January February there is some link, okay, between January March also there is some link, but January April, see, it's decreasing. Okay, if you compare, if you want to see the correlation between January February, there will be something. February March, there will be something, temperature. March April, there will be something. So if you take one lag, there is some correlation. There is a correlation between the temperature between January and February, February and March, March and April, okay. But if you make it to January March, okay, February April, March May, so I mean when you take 2 months, it will decrease, alpha 2 is decreasing, gamma 2 autocorrelation is decreasing. How about 3? You take 3 month gap, it will decrease further. So do you think it will come down to 0? Not here, because what will happen is, again when you see January to January, there is a high correlation, okay. If you take 12 month, if you take 12 month here, from this to this, If you draw the graph also, if the January temperature whatever it is, okay, if you draw a graph, what will happen? The link between this to this, January 2001, 21, January 2020, it's 1. Again, what will happen? This will be 1. Here, this is 1. January 2020, January 2020, that is 1. Okay. Now, February 2000, sorry. Now, when I say 12 month gap, okay, January 2020, January 2021, again there is a very high correlation, the temperature high correlation. So if you take 12 month length, 12 month here, after 12 months it will repeat again. This will be like 13 month. If you see, I'm not saying exactly, it will be like row 1. You see January 2020, January 2021, like that. 1 month you go, then you take the lag 13 month, okay, this one to this one, January 2020 with February 2021. That way if you go 11 month, okay, lag, then also this will be like this one, okay, whatever is here, they will be alike, because ultimately we are comparing January and February temperature, right? So January, February temperature, so you consider 13 month lag. So this is coming once again, this is called, there is a repetition here, okay, there is a period here. After that period it will repeat, it will not come down to 0. That is what you need to understand. I will bring the graph and the whole graph and discuss more in the next class. Just remember that it's not that once it will decrease, it will go down to 0. And remember, this is not stationary. Whatever I showed you just now, this is not stationary. I mean, the temperature recorded, this stochastic process is not stationary, the temperature, okay, because we see it's repeating. Seasonal, you can say, the seasons, we have different seasons, they will repeat. It should come down to 0. That is what you need to observe here. We'll do more about this as well in the next class. I want to end the class with one more example. Now, suppose I will write this AR1 process, 0.3 xt minus 1 plus ET. Then I will write 0.3 or maybe 1 upon 5 xt minus 1 plus ET. If I write xt is equal to 2 xt minus 1 plus ET, then I will write xt is equal to 5 plus 0.2 xt minus 1 minus 5 plus ET. If I write all these are all AR1 processes, okay. So now remember, we know that if alpha more less than 1, then the processes are stationary. And if you see the question, in many cases this must be mentioned, assuming the processes they have infinite history, okay. So when students see this, they ask what is infinite history, assuming the processes they have infinite history. This means they are running from a long time. Okay, so this means the processes are running since a long time. Now that becomes stationary. What happens is, initially there might be a lot of fluctuation, okay, like this, lot of fluctuation, but now suppose this is present, now it becomes stationary, okay, this way. So we'll not worry about the past and we'll check only if alpha mod less than 1 or not. So because alpha mod less than 1, this is stationary, this is stationary, this is not stationary, this is also stationary because this is mu. Okay, alpha is here. In two ways we write. So this is another way of writing AR1. This is extremely important. Now you tell me, I have a question for you. Now you have to tell me whether this is stationary or not. Suppose I write xt is equal to 5 plus 0.2 xt minus 1 minus 4 plus ct. Then how can you decide this is stationary or not? Then how can you decide this is stationary or not? You have to match. Okay, this and this you have to match. So can you make it 5? That is the question. I minus 4, can we make it 5?
Find xt minus 1 and substitute there.
What we'll do is I will write forcibly. Okay, xt minus 1 minus mu plus ct, then it will be mu plus 0.2 xt minus 1 minus 0.2 mu plus ct, so mu minus 0.2 mu, that is 0.8 mu plus 0.2 xt minus 1 plus ct. Now if you write this one, this is 0.2 xt minus 1, that is fine, and here 5 minus 0.8, right? 5 minus 0.8, 0.2 into 4, 0.8, that is 4.2. 4.2 plus 0.2 xt minus 1 plus et. So 4.2 must be equal to 0.8 mu. 4.2 is equal to 0.8 mu. So what is mu? Mu is equal to 4.2 divided by 0.8. What is that? 21 divided by 4, right?
5.25.
What is that?
5.25.
5. Are you sure?
Yes, sir.
Okay. 5.25. Now I can write this way. Okay, I can write this way. This one I can write this way. You can check, okay, that they are the same. 5.25 plus 0.2 xt minus 1 minus 5.25 plus et. So if you see, finally this remains 0.2, so it will not make any difference. They are the same, these two are the same, so this is again stationary. That will not create a problem. The only problem is if I ask you this one. Suppose I will say 0.2 xt minus 1 plus 0.3 xt minus 2 plus et. Then you will have a problem. Though this mod is less than 1, this mod is less than 1, we are not sure. This is AR2. Whatever I discussed with you today, they all are AR1. So for AR2, we have not derived anything. Alpha mod less than 1, that is applicable only for AR1 processes. Only for the processes where there is a one-step dependency in terms of this xt is equal to alpha plus xt mu, or maybe alpha xt minus 1 plus mu. Only when you have one-step dependency, then only this will work. If you have a AR2 process, AR3 process, AR4 process, or higher order processes, for them we have different way of managing. Okay. And for ARP, when P is greater than 1, we'll do next time How can you know whether A or P processes where P greater than 1, they are stationary or not? If you want to know, we'll have another class. In the next class, we'll continue. Okay? Class is over for today. Thank you.
Thank you, sir.